sizing in accordance with AS 1684? Yeah? That's what we're doing. That's what today's about, that one little sentence. So what we're going to do in 1684 is we're going to start at the back. We all know when we build, what we actually do when we build is dig a trench in the ground. We fill that trench full of concrete. Then we get a concrete slab. We put a concrete slab on the top of it. Wall frames, roof frames, so on and so forth. We work our way up from the building. For the purpose of tie down though, we're going to work backwards. Okay, so you're starting at section 9 at the back of 1684. Then bracing is section 8. And member sizing is basically everything that comes before that. So the first step is determine whether the fixings are nominal fixings or specific fixings. What you do to do that is a special chart we go to, and nominal fixings is quite simple. If it is a nominal fixing, that means there's really no load there, no uplift load. So all we do is go to a specific set of tables and just grab a connection from there, which I'll deal with in a minute. If it's specific fixings, then you need to go and work out and do an actual calculation for that connection and work it out. Now, just quickly, any of you here from North Queensland, from up north, you won't have to worry about nominal fixings up there. Your wind pressures are so high, everything's specific, so everything's got to be calculated. The guys that are using non-cyclonic N2 tiled roof, the majority of N2 tiled roof stuff is nominal fixings. But once you determine if it is specific, we don't worry about shear, we only worry about uplift at this point. Because once you provide the correct uplift connections, it will generally take care of shear. And that's the reason we just put that aside. Okay, from a tie-down point of view, we don't really worry about it. Once you understand that we have to calculate it, do a calculation for uplift, you then need to determine the uplift load width, and not or area, and area. So area is square metres, yeah? So you need two dimensions to work out that square metre. So you need what we call ULW, which is uplift load width, and spacing. And I'll explain this in detail to you in a minute, but it's called tributary area, which means the area contributing to uplift of that connection. Once you determine the load, you've then got to determine the force, and I'll give you some pretty simple formulas for that. So once you determine the force, that is the total uplift force on that connection. So we know, we've actually calculated what that force is. Then we go to a specific set of tables. It says there determine the joint group. I'll explain joint group to you in a minute. It's quite simply the ability of the timber to hold a fixing. Okay? Very simple way of explaining that is if I get a nail and drive a nail into a piece of pine, I can just go up there with my claw hammer and pull it out, yeah? What about putting a nail into a piece of ironbark? If you can get a nail into the piece of ironbark in the first place, unlike me, I can't, not very good at that. But if you can get it in there, what are your chances of getting that nail out? Zero. Break it off virtually. So the ironbark has a very, very high ability to hold that fixing. Therefore, you don't need a fixing. You might, instead of using a deformed shank nail, a twist shank nail or something like that, you'll only need a plain shank nail. So that's why we need to know about joint groups. And then we go and select the tie-down connection. And basically the connection, there's a whole series of tables that we need to go through and pull apart. But basically, all you need to do is, if I've calculated 2 kilonewtons of resistance for argument's sake, we need to go and find a connection that is equal to or greater than that 2 kilonewtons of resistance. It's as simple as that. And then, once you've selected the connection, what you do is you go back and just check that with your bracing. Now, I'll just apply this bit of common sense to you. Here's my bracing panel, okay? Now, it doesn't matter what the resistance of this bracing panel is, but if it's not tied down, it can do one of two things. It can do this one, okay? Sliding. Or it can do this. This is called a moment of rotation. So the resistance required to hold a bracing panel down, generally, because of the weight of the building, and I use the term generally, will avoid any uplift resistance. It will exceed the requirements for uplift. Fixings are required at all interfaces. In a 2-storey building, excluding the roof connections, there is actually 16 of these connections, not including the roof connections. So if it was a stick roof, there is more than 16 connections that you have to take care of. And in a lot of cases, they will generally be the same. They'll be very close, depending on your wind classifications. Where they will vary, in particular, is when it comes to lintels, with your lintel connections, depending on the size of your openings. And as we all know these days, these sliding door and multifold door openings are getting bigger and bigger and bigger. So that's probably where you're going to have to calculate it. Wind classification. The first step is select the wind region. Now, the majority of Australia is wind region A, and it's about the distance between the coast and where you're actually building the house. Wind region B starts at about 27 degrees latitude and goes, it starts at 50 kilometres from the coast. It's between 50 and 100 kilometres from the coast. Starts at 27 degrees and goes right around to 27 degrees latitude in Western Australia. Wind region C is the 50 kilometres right on the coast, and I think it starts up at Bundaberg and runs right around the top, right around to Darwin, and right down to, I'm not sure, somewhere further down south. And then there's wind region D, which is over in the Carnarvon area in Western Australia. And it's the highest risk because it's about cyclones. If you think about the water, there is no resistance to the wind where it's coming off the water, okay? So that's what that's about. It's selecting where the house is in relationship to the coast. The majority of Australia, as I said, is wind region A because the winds from the south are nowhere near as strong as what we could expect from the northwest or the northeast. Then you select the terrain category. And terrain category is quite simply about surface roughness. You think about an open airfield or a sea coast area where there's not a lot of trees, that has a very high risk terrain category. In other words, the wind can get across there a lot quicker. But you must have a lookout where you look over the coast here somewhere. You always stand at the top of these lookouts and you can feel the wind rushing up underneath your shorts, yeah? Coming up from down low. If you think about this here as being an escarpment, and you're standing up here, and the wind's coming across, if you think about wind arrows hitting there, say you've got a wind pressure here of 10 kilopascals, this is 10 kilopascals, this is 10 kilopascals, so in total, if you were to add them together, that becomes 30 kilopascals. Because you've got the ground down here, the wind can't go down. It's a bit like water, it's going to find the path of least resistance. So what the wind actually does is compresses like that. And the easiest way out is up. And that's why when you're standing at the top of the lookout, you're getting all this wind rushing up from you underneath. There's no wind around, but at the lookout, you're getting this wind coming up from underneath you. It's because the wind's compressing there at that point. So if you're building a house on the top of a hill, what you're getting is all the wind hitting the bottom of the hill, heading up the hill and compressing. So when it gets to the top, it's a higher risk at the top of the hill than it is at the bottom of the hill. So that's why it's important you understand the topographical class. And the last thing is shielding. Think about the spinnaker on a sailing boat. If you had a spinnaker at 90 degrees to the boat, which is the ultimate, it's going to pull that boat along, depending on the weight of the boat, but that's where it's most efficient, for want of a better way of wording it. I'm standing here, I've got this hot wind blowing at me, but if I was to go around behind this, this would shield me from that hot wind. So that's what shielding's about. If you're building a house in the middle of a paddock out at Gundawindi, for argument's sake, there is no shielding there. Let's say you're talking about some of these, I don't know what you call them, these acreage suburbs that have scattered, like they're 2.5 acre blocks or 2.5 hectare blocks. They have some scattered eucalypts around the place and maybe a farm shed over here and another house that's 500 or 600 metres that way. That's what we call pastoral shielding. In other words, the house can still get some of that wind on it, but it's slowed down because it's got to, change direction and zoom in and out between the trees. And lastly, if you've got a house in the middle of, pick a suburb in the middle of Brisbane, or even in the middle of the Gold Coast over here at Southport, where you've got all these other houses around it, it's full shielding. So that affects the wind classification. Can I ask you to go to page 168, table 9.2. Now this is what we were talking about before, whether we talk about nominal and specific. So this is this table you should go to first. Now, you'd be crazy not to check this first, because if you've got a nominal connection, that means you don't need to do any work. You quite simply, when you find out it's a nominal connection, you go to table 9.4 on the opposite page there. And what you'll see with table 9.4, it's actually broken up into 3 different areas. One is floor framing, one is wall framing, and when you go over the page is roof framing. So all you do, if you wanted to connect your top plate, a rafter top plate, obviously that's a roof framing connection, you just go to the roof framing section on page 170 or 168, depending on your book. You see there where it says rafters to plates or ring beams, coupled roofs. A coupled roof is a stick roof. A non-coupled roof, that's a coupled roof, or a truss roof, that's a coupled roof. A non-coupled roof is where you have this and you've got a supported ridge which is supported either end. So there's nothing in the centre of that to stop that roof from sliding out. That's non-coupled. Okay, so if it was a coupled roof or a stick roof, you'd go straight there where it says coupled roof, and all you've got to do is put 2 skew nails in there. 2 3-inch skew nails, that's all you need to hold the roof down. If it's specific, we're going to do a calculation. So back there in 9.2, what you'll notice is generally anything of N3 or above is a specific connection which you have to calculate it. And once you understand the formulas, it's quite simple. Right, table 9.5. This is your go-to page, your go-to table. This is where you get your pressures from. Now, let's look at the top row, and it talks about battens, roof battens. And this is about selecting where the pressure is applied in the building. And we talk about the building in the elevation of the building. Okay, so if you look at it, we're talking about where it is in relation to the height of the building. As I said before, it matters whether you've got a sheet roof or a tiled roof because it contributes to uplift. But if you think about it, the uplift up there at the top of the building, because there's not a lot of weight at the top, will obviously be significantly higher than it is at the bottom plate, because you've got the weight of the building on top of it. So as you go down through the building, the pressure actually reduces, and you can see that in the table. You look at N1 tile there, even in the second row, it's just got that little blank in there, and where it's got that blank, that means you just go straight to table 9.4 and get a nominal connection for it. So all you need to do in N1 tile is tie your roof battens down to your roof frame, and everything else is a nominal connection. Okay, it's as simple as that. Where it's just got that little blank there, that means nominal connection. So the first row is for battens. The second row is for all your roof connections, all your wall frame connections, right down to your stud bottom plate. So any connection that's being assessed in your wall frame or in your roof, you get the pressure from that second row through the building. Okay, that's what that description basically means. And I'm sorry, I haven't got any better way than explaining that to you. If, say, you were doing a lintel connection, a lintel to the stud which is actually connected to the plate, which we'll have a look at in a minute, you select it from that second row. If you're doing your plate to your first floor, it says single or upper story, it uses the word single or upper story, your upper story bottom plate to the floor frame, you get it out of that third row. Or if it was a single story building where you've got your bottom plate connected to the slab, again you get it from that third row. So in a single story building, you'd actually be using 3 rows out of the table. You'd be using row 1 for your batten connections, row 2 for all your roof frame connections and all your wall frame connections right down to your stud bottom plate connection, and row 3 where your bottom plate was connected to the slab, if it were a slab. Okay? It kind of gets a bit... I talk about rows. Okay, I'll ask you later on which row would I get the pressure from, and you should be able to say 1, 2 or 3. And so what that means, again, just pulling that apart, the connections that are in that second row are these ones, all your roof framing connections. So the floor frame to supports is first floor joist to top plate, lower story wall frame to floor frame or slab, top plate to studs, studs to bottom plate. So this is what is inside these rows. If you just picture it, look into the elevation of the building. Try not to look at it from the top. The pressure table needs to be looked at from the side of the building. And the last row is obviously your ground floor bearers to joists, piers or footings. Now, batten connections. You know when your plane comes into land and you watch the wings, the front of the wings extend out and the back of the wings extend out and make this big shape like this? This is called the Bernoulli effect. So your wing actually looks like this, okay, when they come into land. You think about the wind. Now you have to understand that the wind has viscosity. Think about it like oil in your engine. The wind doesn't come up against the side of this building and stop and turn at 90 degrees and then get to the roof and turn and back across the top like that. It doesn't do that. What it actually does is it flows. So the wind will flow up over the top, it'll compress and flow up over the top of the wing like that. But when it runs through here, because the plane's going so fast, what it does in this area in the centre of this hollow section here is create a vacuum. And because it creates a vacuum, it sucks air into it, like so. And this is what gives the plane uplift at slow speed. It's the Bernoulli effect. Okay? Does anybody... There is some faces I can see in here that were alive in 1974. There's some that weren't born then, but most of us were. You'd remember Cyclone Tracy and Darwin. The scars of Cyclone Tracy, I can tell you, are still up there now. One of the things that destroyed Darwin at the time was the Bernoulli effect. Darwin had such a problem with waterproofing up there of their roofs, what they did was create roofs with no joins in them. Does anyone know what that was called? A roof with no joins in it? Not a trick question, it's called a wrap-over roof. Remember the wrap-overs? You use graded purlins, you'd start at 150s at the wall plates, work into the centre where they're 300 high, so you've got bugger all full length, and they just put a full sheet over the top with no ridge through the centre. The problem with a wrap-over roof, if you think about it, is that you've got this building, they had 1200mm wide eaves, and the part of that too was to stop a lot of wind getting in around the windows, and they had the roof that come up, and it was something like that. I'm not very good at this drafting size things. That was kind of what the roof was like, nowhere near as high as that. Remember what I said before when we were talking about topographical class, about the wind arrows hitting the side of the building? And let's assume, we'll use this magical number of 10 again because it's an easy one to work out. Each one of these wind arrows has a pressure of 10 kilopascals. It's got nowhere to go because it can't come down here on the ground. The ground stops it. It can go sideways, but it's still compressing. It's still giving it resistance because of this wind viscosity, for want of a better word. So what actually happens is it all compresses and it comes up here underneath the eaves here till it reaches a point where it's compressed and it comes up and it does this. Again, as I said, the wind doesn't come out and go just 90 degrees and back across. Because of this viscosity, it forms this, and I use the term loosely, Bernoulli bubble at the outer edge here. Then it comes across here and it does the same again, creates a Bernoulli bubble at the side of the building. So what you're getting here is an uplift at that point, an uplift Bernoulli bubble. And again, don't try and Google my words, I'm just trying to keep it simple for us builders. And here you're getting what we call a racking bubble. So this one's more focused on bracing, trying to pull the building over or rack the building. This one here is more focused on uplift. There's only two wind directions. There's short side of the building, that way, and from the other end, that's one wind direction, and long side, so from this end and that end. So when you think about this one, wind comes from this way, you're also going to get wind coming from this way. So what you're going to end up with is another Bernoulli bubble where it all builds up here on this side, coming across, and around here you're going to get another one here. So you've got these vacuums here and here. And if you think about it, some pointy head, to use the technical term, has actually sat down and calculated this area of high risk as being 1.2 metres in from the edges. Okay? Now, if this was a wrap-over roof or a gable end roof, it's still an edge. If you think about it, the wind comes up. Just pretend this was a gable. The wind comes up, compresses against the building, comes up over the edge like that, and creates this 1.2 metre wide strip of higher pressure, because you've got this large vacuum on the side of the building. So this is very important. I'll get you to write this down. Batten connections. Edge battens are all connections within 1.2 metres of the edges. Edges are not quite what you think. Edges are hips, ridges, fascias or barges. So I want you to record this, please. It's very important you get that embedded in your head. The only difference between the two is the pressure. The tributary area is going to be the same. It's the pressure that's different. That's very important you understand that. People get this confused regularly. Now, when you have a look at what I've just said, and that bottom line, the only difference is pressure, you have a look now at the difference in the pressure on table 9.5. Let's look at N3 sheet roof, for argument's sake. Yet pressure on the edge of the roof is 2.92 at this point. So N3 sheet. On the edges, just here, it's 2.92, and that's KPA, little k, capital P, little a. And in the general area, it's 1.57. So this area from here to here, the pressure is 1.57 KPA. And you can thank Dr. Bernoulli for that. If you think about it, the area surrounding a batten connection out here, let's say our battens for a tile, for a sheet roof are at 900 centres, okay? They're 900 centres over here in the edge area, and they're at 900 centres over here. So the area is the same, okay? You will get some cases in some industrial buildings where I actually was standing at the Big Green Hardware store the other day, and I looking up at the purlins on the roof, and over towards the edges, because they had them out here at 1.5 metre centres, over on the edges, they had them at 750 centres. Thank Dr. Bernoulli for that. When you're doing battens, a batten connection, you work the area out once, and we'll do an example of this today. You work the area out once, but then you've got to do two connections. You've got to do two calculations for the connections, one for edge battens and one for general area battens. And when you actually do that connection, you'll shock yourself. You realise those who have been using roof tiles, your tiler has not been doing it right. In any of you working N2 tile roofs in Brisbane or around here? No? Yeah? Have you ever seen your roof tiler go down to the car and get a deformed shank nail out for your battens on the edge? Thank you, you answered my question. And he should be. It doesn't happen. All right. Now, these are the three methods of calculating. I explained this briefly before. The first method is the specific method, and that's what we're learning. The second method is the nominated method. Now, just forget about the nominated method. Not nominal, nominated. Just forget about it. I don't want you to go there. And the third method is the evaluated method, which is what you're doing now. You're shelling out the readies, giving it to some engineer to tell you the same thing over and over and over again. The specific method, please write this down. These are the go-to formulas. The specific method is the calculated method. Force equals pressure times area. Area equals spacing times ULW. This here, if you think about the load path, 5 kilonewtons comes across here and down here. 5 kilonewtons comes over here like so, yeah? Now, what is the load width in this case? And it's half of whatever that distance is. So the load width in this case is half of there. Do you understand that? So let's say that in total was X. This here will be X, not 8, X divided by 2. That's what the load width is. Now that's beam design. I want to keep it really simple because we're builders. We're basically simple people. Don't be offended by that. This is tie down. Just reverse the directions of the arrows. It's not that technical. In theory, if I had a crane here and I had say I had a spreader bar with 5 kilonewtons or 500 kilos this side, 500 kilos that side, obviously I'd be lifting 1,000 kilos in the centre. If I could get it exactly right in the centre, I could lift that. That's all tie down is. And one more little secret, if it's a secret at all, this is bracing. Bracing, just think about a vertical beam. Half the load goes into the roof, half the load goes into the floor. That's bracing. Just keep it really simple. Dumb it right down. Go back to basics. That's all it is beams. And you guys understand beams. I'm going to do my first tributary area drawing for you. I'm going to do a batten connection straight up, which is pretty basic. I'm going to draw 3 rafters. And they're going to be at 600 centres. Whoops. Now I'm going to draw 3 battens. And I'll do a tiled roof. They're going to be at 330 centres. Now I use 330 because that's what the standard thinks. They reckon, the standard reckons our battens for tiled roofs are at 330 centres. The connection I'm going to assess is this one here in the centre. Now believe me on this, the formula for ULW in this case, and ULW is parallel with the direction of the rafters. There it is up there. The rafters or the trusses, is half the distance between connections plus half the distance between connections. Now this is a key. I don't want you to think about the distance between your batten spacings or the distance between your rafters, and that'll become evident later on. I want you to think about where your connections are. Think about connections all the time. So it's half the distance between connections plus half the distance between connections. Okay, that's the first thing. Spacing is perpendicular or at 90 degrees to your rafters or trusses. So your spacing is this way. And the formula for spacing in this case and in all cases is exactly the same. It's half the distance between connections plus half the distance between connections. You don't need to write that formula down yet because I've got a slide on that in a minute which will give you that formula. Half the distance between connections plus half the distance between connections. So that shaded area there is the tributary area of that batten connection. What part or the area that's contributing to suction or uplift on that connection? That's it there. You can actually do it mathematically, but I'd encourage you to do that drawing first or do that sketch first. You'll see there, my drawing skills are not great, crappy in other words, but I've just done a single line sketch. I haven't used AutoCAD or even a ruler or set squares, just do it that way, and I can get into my builder's head now exactly what the hell I'm talking about, the tributary area. Okay? So they're 2 rules that you need to understand. ULW is parallel with the rafters. Spacing is perpendicular or at 90 degrees. These are golden rules. Force equals pressure times area. Area equals ULW times spacing. So it's that dimension there times that dimension there.
Is that the same when it gets closer to the edge?
No. And this is the confusing part. That's why I went back before. You've got to get out of your head the idea that this is an edge. It's not an edge. It's all connections within 1.2 metres of the fascia, barge, hip or ridge. Let me just explain that a little bit more. Here's a gable end roof. Okay? Ground, ground. This is why a gable is an edge. Say I've got 5 wind arrows. All those 5 compress. Sorry, I should be using red. All those 5 arrows compress and we get a big Bernoulli on the edge of the building. Okay, so that's your 1.2 metres. So that's a barge. That's why a barge is on an edge. You have a look at a stick roof. Badly built stick roof, but it's a stick roof nonetheless. Where you've got the wind arrows coming on the side of the building. So what's actually happening, you're getting a small Bernoulli happening here. So that's an edge within 1.2 metres of the fascia. And then when it comes up the roof, it goes over like that because of this viscosity, over like that and back down. So there's another Bernoulli as well. So that 1.2 metres at the ridge. And a hip would be exactly the same. As you got the wind blowing over the side of the hip, it's going to create a Bernoulli on that. So that's what edges are. Edges aren't the fascia or the barge. They're also the ridge and the hips. Okay, you just got to kind of stick with the definition I give you back there at that other slide. Every connection within 1.2 metres. You just work out, technically what you're saying is, right, if this was the fascia here and you've got a connection there at that point, it's really only half that tributary area, isn't it? But because we need to wipe that out of our head, we just work on this one. We'll do one area, which will be 330 by 600, and that'll apply over the whole roof, assuming your batten spacings are the same. We're doing construction in heaven. Your batten spacings will be the same. It'll be perfect. Okay? The area carried. So each connection supports an area defined by ULW and spacing. ULW stands for, up there, uplift load width. That's what I was trying to show you on that beam before. Half of X was that load width. That's what ULW stands for. Lengths are always in plan. Thank God. We don't have to worry about the pitch of the roof in this case. It's in plan. So when you're working out your tie-down connections, you only look at your plan views. Don't worry about your elevations. It's only plan views we're concerned about. For those guys who have a 2010 version, go to page 171. It looks like this. It's this page here. I'll get you to go to that page. Now we'll look at the bottom diagram first. Now, as I said to you before, what I want you to do is focus on beams. Just think about beams. And I'll show you a beam of a roof, of a truss roof now. And it's actually a lot simpler than you think. There's the beam of a truss roof. That's it. I'm going to put a point load in the centre, and I'm going to put a point load here, and a point load here, just for the purpose of demonstration. If I was standing out on here, nailing the fascia on, which I'd never do, but just say I did, where would my load go? Think about the path of the load. Back down here, isn't it? Yeah? And then, I don't know, if I was standing in the centre here, where would my load go? Half the load would go this way, and half the load would go this way. Same here. This was 5, that's 5. This was 10, that's 5. 5 plus 5 at this point is 10. This would be 5 plus 5, providing that was 5. So that's what you've got to think about. Go back and think about beams. So the load width in this case is half the distance between there and there, plus this. Have a look at that bottom diagram on page 171 or 169, depending on your book. Look on this side of that diagram. Can you see those ULW lines? It goes from half the distance between the wall frames, or half the distance between connections, plus the overhang. Can you see it there? See how it includes the overhang on the outside? Now apply this back here to this beam. So the load width in this case is that distance there. Half the distance between connections plus the overhang. Hopefully that's on the next slide. Now that's on the outside wall. So that's what I want you to write down. ULW, and then in brackets, outside wall connections equals DBC divided by 2 plus the overhang. DBC being distance between connections. I'm not going to go any further until everybody's got that written down and got a big circle around it and highlighted it. Very important. Does everybody understand when I use the term stick roof? Does everybody understand what that is? Pack of timber, a pitch roof, yeah, or a conventional roof. Pack of easy for me to say, pack of timber, dumped on the footpath out the front, stick by stick, we bring it in, put them all together and make the roof out of it. That's a stick roof. If you have a look at that second diagram on the right-hand side and you think about what I said about connections, think about what I said about connections and not spacings. If you have a look at this one here, this rafter is connected at the top plate and its next connection is where it meets the underpurlin. Can you see that? And again, you look at the lines above it and what you'll see, that line there that's outlining what the ULW is on that outside wall is halfway between where the rafter is connected at the top plate and where the rafter is connected at the underpurlin. So again, the formula's there. Half the distance between connections plus the overhang. Focus on your connection. So there's two formulas for ULW and that's them there. There's the formula for outside wall connections, that's the exception. It's just the outside wall ones, which is DBC divided by 2 plus overhang. And all other connections, so whether it be ridge or underpurlin or whatever it is, the formula is DBC divided by 2 plus DBC divided by 2. And that's why we use that formula here, because a batten rafter connection is not an outside wall connection. So when you're doing an assessment of a connection, the first step you take is you look at it and you say, is this an outside wall connection? Yes or no? Simple as that. Is a lintel plate an outside wall connection? Yes. So the formula I use is DBC divided by 2 plus the overhang. Okay, that's basically how you do it. Is a batten rafter, is that an outside wall connection? No. So the formula I use is DBC divided by 2 plus DBC divided by 2. And all the time with spacing, the formula with spacing is DBC divided by 2 plus DBC divided by 2. So half the distance between connections plus half the distance between connections. And if you apply that, half of 600 plus half of 600 equals, that's it. Half of 330 plus half of 330 equals 0.33. So then you take that up here and you go area equals ULW times spacing. And I'm not going to do it because I've got that in a worked example that we come up with. So it'll be 330 times 600, which will give you 0.198. And then you revert back to this. I'll show you how that all pulls into place soon. Now this is an example of a truss connection. Question, is a truss top plate an outside wall connection? Yeah? Which formula do I use? Exactly, DBC divided by 2 plus overhang. Okay, the truss is sitting on that wall and sitting on that wall. That's about 10 metres. Half of that is 5 metres plus the overhang. DBC divided by 2 plus the overhang, that's how I come up with it. 600 was the spacing in the connections. Half of 600 plus half of 600 is 600. 5.6 times 0.6. That's as simple as it gets. So here's the information I was given. N2, single story, truss spacing 600 centres, roof span 8 metres, 600 overhang, sheet roof. So there's a couple of critical bits of information there. First of all, N2, sheet roof are the critical parts of it. Secondly, where it says truss spacing at 600 centres, so obviously that's the distance that the trusses are apart. So that will be the distance between connections, 600. And the roof span is 8 metres. What that actually should say is the distance between the connection on that side of the building and the connection on that side of the building. So already you can see the pattern forming here, I hope. Can I ask you to go to table 9.5, N2, sheet roof. Now, it's not a batten connection, so it'll be a connection in that second row. Okay, N2 sheet roof. Can you see the pressure there, 0.74 kilopascals? Yep. That's how we select it. Is everyone good with that? So there's the pressure there, 0.74 kilopascals. The ULW equals half the distance between connections, so there's that there, plus the overhang. The overhang 600, so it's 4.6 is the ULW. The spacing we know is 600, half of 600 plus half of 600 equals 2.76 square metres. And then we go back to this initial formula, force equals pressure times area. Force equals 0.74 times 2.76, and that gives you a pressure, uplift pressure of that connection of 2.04 kilonewtons. That's how you pull it together. What'll change whether it's a sheet roof or a tile roof? What part of that? Yeah, the pressure. The pressure we selected from that table. The area is still going to be the same, the tributary area is still going to be the same, but the pressure will vary. Okay? To determine the connection, we need to know the joint group. All right? So we need the connection type and the force and the joint group. They're the three things we need to pull together. I just explained to you about joint groups. It's basically the capacity of the timber to hold the fixing, varies with density. Okay, if you were to do a timber wall frame, what would the framing be? 1945. Yeah, hardwood? Pine. Okay. Now this is important. I want to make this distinction. Which joint group do you reckon governs in that case, the pine or the hardwood? Exactly. The weakest joint group governs. If you're using pine frames, we work on JD5, okay? There it is there. JD means seasoned timber, which is what most of your timber is. And most of the stuff we're using these days is MGP. So we're all going to work on MGP 10 for our task 57. MGP 10, JD5. And you'll notice there that the difference between North American Oregon and Oregon from elsewhere is a change in the joint group. It goes from J4 to J5. Now when you go up the top, it talks about seasoned softwood. And it talks about heart-in material and other material that's free of heart. Now I just said to you about the mechanical grading system, MGPs. Computers control MGP systems, not human beings. All your F gradings and everything else is visual stress grading. So they can look at a piece of timber and they can look at the end grain of it and determine whether it's got heart in it or not. A computer can't do that yet. It will get there, believe me. So what we want you guys to assume is that every piece of pine you're going to use, because would I be right in saying the majority use MGP? Okay, as your framing, assume it's got heart in it. Now the heart, just to, by way of explanation, I'll tell you a little bit about trees. When you're treated hardwood is kind of a bit of a misnomer, because you can only treat the sapling of a piece of timber. You can't treat the heartwood. Even in pine, it won't accept the treatment or it won't hold the treatment. Now a pine tree has a heart about that big proportionately. So it's only about 20% of the section size of the timber. But a piece of hardwood has a sapling about that big. So the moment when you get a piece of treated hardwood, the treated hardwood is what we call an envelope treatment. It's just basically a treatment that goes around the outside of it, because it's likely that the piece of hardwood that you're using comes from there, which is all heartwood, which doesn't accept treatment. So providing you don't cut that piece of hardwood, your treatment's all good. And that rarely happens. And that's why we use treated pine quite a bit, because a treated pine log, this section here will have heart in it, so it's not treated correctly. But if we can get a section from out here, that's treated correctly, and you can cut that and it's no problems. All right, so that's the difference between the two. So what we're going to say to you is, the computer can't look at that piece and go, oh, that's got no heart in it, we'll separate that one out this way, and this one here has heart in it, we'll keep that one in this pack here. Therefore, this is J4 and this one's going to be J5. The computer doesn't do that. So we want you to work on this one here. Every piece of pine you're going to use is going to be JD5. Seasoned softwood, heart in. Joint groups. We just discussed joint groups. Hopefully you understand that. Now we're going to talk about connections. So on that flow chart, we're down at the point now where we've calculated the value of uplift at that point. We've determined what the joint group is, and now we've got to go and find a connection that is equal to or greater than the calculated amount. So on our example back there before, we were 2.04 kilonewtons or something like that, I think it was. So we've got to go and find a connection that will resist that 2.04 kilonewtons. They start at table 9.15 and go through to table 9.25. The first one we're going to pull apart is Batten Connections, which is on page 210. Now, this is a national standard. The standard you're looking at, and it's a national course that you're undertaking. We've got national licensing coming up in 2013. So it's a national standard. What you'll see there with the type A connection is there is a 50 by 25 batten. Now, any of those who have done a tiled roof, can I ask you when you last used a 50 by 25 batten? And the answer is never. Okay? But in Western Australia, a 50 by 25 batten will span 450 centres roofs in hardwood. It will do that. So that's what that connection's there for. But for the purpose of us, we're not going to use a type A connection. We're going to use a type B connection where you've got 75 by 38s or 50 by 38s. That's what it is assumed you're going to use. Now, how these tables work, and they're all the same, first of all, you must read the heading. And the heading in this case says uplift capacity of roof batten tie-down connections. So this is where we should be looking for a batten connection. Secondly, we've selected our joint group, which is down the side here. You'll see the joint groups run down the side, and we've all agreed that we're going to use JD5. Okay? So you start at the top, you work out what the value is, you run down there, and we can't start at A, we start at B, until you find a connection that is equal to or greater than the required value. Now, as by way of example, for a tiled roof, and there's a couple of things here, I'm setting you up for a fall here, but it's so you learn. I want you to find a connection for me that will do 0.29 of a kilonewton. Will give me it's got to be equal to or greater than 0.29 of a kilonewton. So start at the top in JD5 at type B and see what you come up with. Okay? So you start at JD5, and what you'll do is start here, and we're after that we've calculated 0.29 of a kilonewton. So I start there and I go, one plain shank nail won't do it, 0.21. So you go to the next one, and you'll see two 3.05 nails will give you a resistance of 0.42. So that's equal to or greater than that 0.29, isn't it? But look at this little note over in the corner. See the note there under my finger? What it says is 2 screws shall be used only with 75mm wide battens. Now that's a mistake in itself. There's a typo there. Cross out the word screws and write nails for a start. So you can only use 2 nails in a 75mm batten. So we can't use that connection. We have to go down. So you come down here, huh?
2006 doesn't say, it says nails.
Yeah, it says nails in the old standard, but it's screws in the new standard. This is mistakes, I told you. It was a pretty average document. So you've got to come down, and you'll see that 175 by 3.05 deformed shank nail is suitable for that 0.29 of a kilonewton resistance. So that's what it's all about. There's all these alternatives inside these tables.